Good day. In this video, I am going to introduce rotation of a rigid object about a fixed axis. This time around, we will no longer ignore the rotation of objects. In fact, we will focus on spinning motion of objects, and we will focus on rotational motion of rigid objects. So let me first define what a rigid object is. A rigid object is one that is non-deformable. That is, the relative locations of all particles of which the object is composed remain constant. So all real objects are deformable to some extent, but our rigid object model is useful in many situations in which deformation is negligible, right? So I'm going to introduce some analogies to our linear variables. First, we talk about angular position. I don't know if you remember that we once talked about position, right? That was referring to more related to linear situations or objects moving along one axis, the x, y, or even the z. So in this figure, to the left, you see a Blu-ray disc. I don't know if those things still exist. This disc rotates either clockwise or counterclockwise about a fixed axis, which is perpendicular to the plane of the figure, and it passes through O. So there is a line that is perpendicular to your screen that passes through O, point O. We call that the fixed axis. So the disk has small elements, no? You can think of the disk as composed of particles, in fact, infinitely many particles. But let's just focus on point P, a point on the disk, which is located at a fixed distance r from the origin. So if we only focus on point P as the disk moves, you will clearly see that point P rotates in a circle. In fact, every element on the disk not labeled here, maybe there are other points you can label as Q, R, S, A, B, C. All other elements or points in this disk undergo circular motion about the fixed axis passing through point O. I don't know, I'm sure that you remember the polar coordinates, right? So point P, we can represent its location as, or its angular position in terms of polar coordinates, r and theta. R is the distance from the origin to point P, and theta measures counterclockwise from some reference line fixed in space. And our reference line, if you look at the right picture on the right, is usually the positive x-axis, right? And as the disk rotates, the particle at P moves through an arc length S, which is an arc in the circle, the circular path of P as the disk rotates. R is the distance from the origin to point P, and theta is the angular position of point P. Okay. So we define theta as the ratio of the arc length to the radius r. So I don't know if you remember this, no? In your geometry, that angle related to arc length is equal to S over R. And we're rearranging, we have S equals R theta. R here is in terms of meter, and theta It's not in terms of degrees. Theta is in terms of radians. Radians is another unit of angle or angular position, but it is actually unitless. I will show to you now to remind you how you convert from degrees to radians. So 360 degrees corresponds to 2 pi radians. 360 degrees is equal to 2 pi radians. So that's how you convert. So for example, how about 180 degrees? That's half of 360. So what is half of 2 pi? Pi. So 180 degrees is pi radians. And 1 radian is approximately equal to 57.3 degrees. Okay, so the arc length S is equal to R times the angular position theta, which is in terms of radians. It's the ratio of the arc length to the radius, S over R. So to define angular position for the disk, a reference line fixed in space is chosen. Particle at P is located at a distance R from the rotation axis through O. The disk, in this case, is a rigid object. So as the particle moves through angle theta from the reference line, every other particle on the object rotates through the same angle. So if there's another point here, point Q, located somewhere else in the disk, that point will also rotate theta as the point P rotates theta. So all points rotate the same angle because the disk, we model it as a rigid object, no deformation. So to define the angular position of a rigid object, it is the angle theta between the reference line on an object and a fixed reference line in space. Angle theta is the same, it obeys the same role in rotational motion as position x in one-dimensional translation motion. So in one-dimensional translational motion, we refer to the position as x this time. For rotational motion, our position is expressed in terms of theta. So what is angular speed? So as a particle on a rigid object travels from point A to point B, look at that picture, in a time interval delta t, where ti is the time for when the point is at point A, and t final is for when the point rotating is at point B. So delta t. We know how long it takes for the rotating point to move from point A to point B. So we can calculate the angular speed, delta theta. Here, we call that the angular displacement. So the angular displacement. So therefore, our angular speed, our average angular speed, represented by that symbol which looks like a W, that is the symbol omega. Omega sub ABG is equal to delta theta, which is our angular displacement over delta time. So the rate of angular displacement can vary, right? So if a rigid object spins rapidly, the rigid object can reach displacement, certain angular displacement in a short time interval. But if a rigid object rotates slowly, the displacement is reached in a longer time interval. So average angular speed, omega AVG, that is the ratio of the angular displacement to the time interval delta t. It is analogous to translational speed. You remember our average velocity, right? Now we have average angular velocity or angular speed. Now this one is omega only. This is instantaneous, right? You remember we used limits or derivatives also for our instantaneous linear velocity. Now we have instantaneous angular velocity, d theta over dt. Okay. The unit of angular speed is radians per second. So radians per second, rad per second. But actually, rad per second is also equivalent to 1 over second because radians is not dimensional. It almost has no unit. Radians is not a real unit. Why do I say so? Go back here. The definition of theta, S over R. S here is in terms of meters. R is also in terms of meters. Meters over meters is 1. So in reality, the angular position in terms of radians is dimensionless. Okay. So the again, no, the unit is radians per second, but that is equivalent to 1 over second since radians is dimensionless. So omega is positive when angular position is increasing or counterclockwise. And if the angular displacement is clockwise, then that is a negative angular displacement at the same time. This is a negative angular velocity. Okay, let me just try to answer this. A rigid object rotates in a counterclockwise sense around a fixed axis. Each of the following pairs of quantities represent an initial angular position and a final angular position of the rigid object. Each of the sets can only occur if the rigid object rotates through more than 180 degrees. So the answer is letter C. Why is that? For a rotation of more than 180 degrees, the angular displacement must be larger than pi, which is equal to 3.14 radians. The angular displacement in the three choices are, for letter A, the angular displacement in this case is 3 rads, but that's less than 3.14 radians, which is pi, right? Pi, or 180 degrees, right? The other one, this is 2 radians, 1 rad to negative 1 rad. That's 1 rad minus 1 rad. So that's still less than 3.14. This time, 5 rad to 1, that's 4 radians. No? So this one is greater than 3.14. So yun lang. So that ends our video. We'll talk about this in the next video or in our next lesson. So goodbye.